In number 26, we're given the graph of the derivative of f of x from -3 to 3. We're asked to find the relative maximums, minimums, and justify our answers, and find out when the graph of f is concave up. Then we also want to graph this. So we can do part A here. In order to do part A, in order to find a relative max, relative min, we need to figure out when the first derivative changes from positive to negative. So I'm going to go ahead and create a first derivative number line. So we have the graph of the first derivative. On our number line, we need to put our critical values, where the derivative is 0 or does not exist. Since this says y equals the derivative of f of x, that means the y values on this graph are equivalent to the derivative of f of x. The derivative or the slope of f at those given points. So we have zeros on this graph right here at these 4 points. At -2, 0, 2, and 6. At each one of those points, the derivative is 0 because the y value here is 0. So our derivative has to be 0. Those are our critical values. Then we can look at what's happening in between those. Here, the y values for all these points, they're all above the x-axis. So all of those y values are positive, along with these y values from 0 to 2, and these y values from 6 to 7. But then, these intervals, the y value is negative, from -2 to 0 and 2 to 6. Again, since the y value is negative, that means the derivative of f of x is negative. So in part A, we're finding relative maximums and relative minimums, and we want to justify our answers. So if we look at our number line, we're changing from a positive derivative to a negative derivative at -2. So we have a relative max at x equals -2. We also have one at x equals 2. And we're asked to justify our answers. So the reason we know this is because the derivative changes from positive to negative, or f changes from increasing to decreasing. That's how we knew this. That's how we justify our answer. So we can say because the derivative of f changes from positive to negative. And we have relative mins at 0, x equals 0, and x equals 6. Because the derivative changes from negative to positive. In part B, we're asked to find when the graph is concave up. Well, we know a graph is concave up when the second derivative is positive. Well, we're given the graph of the derivative. We need to somehow figure out information about the second derivative. Well, second derivative is the derivative of the first derivative. And remember, the derivative represents the slope, or the rate of change. So basically, we're looking at this graph, and we need to look at the rate of change of this graph, or the slope of this graph, to interpret what's going on with the second derivative. So just like the first derivative, we need to know when the second derivative is 0. Only here we're not looking at the intercepts, because this isn't the graph of the second derivative. We have to look at the slope of this graph. So the slope of this graph is equal to 0 when we have a horizontal tangent line. Slope is 0 at these points, which means our second derivative is 0. So these are the points that we're going to put on our number line. So we have -1, 1, and 4. Then to figure out when the second derivative is positive or negative, again, we're looking at the slope of this graph. Slope of the derivative gives us the second derivative. So the slope of this graph, if we look at this first part, the slope here, use the highlighter, slope is negative. Then the slope from this point, -1, to +1, that slope is positive. Then the slope from 1 to 4, in between those 2 points, the slope is going to be negative, and then the slope from 4 to 7 is going to be positive. So in part B, we're asked to figure out when the graph of f is concave up. It's concave up on the intervals from -1 to 1 and 4 to 7. And we want to justify that. Well, the reason is because the second derivative is positive. Right, our second derivative is greater than 0. When the second derivative is positive, our graph is concave up. The graph of f is concave up. All right, last part, we're supposed to use the information that we got from A and B and the fact that f of -3 equals 0 to sketch a graph. Well, the f of -3 equals 0 just tells us that the point -3, 0 is on the graph of f. So that's kind of our starting point. Alright, so we want to look at these number lines. Here we realize from the first derivative number line we have a relative maximum at x equals -2. So at -2, I'm going to put a point up kind of high because we're going to have a maximum there. We have a minimum at x equals 0, so I'm going to put that point a little bit lower. Maximum at x equals 2, so I'm going to put that point up. It doesn't have to be the same height, it just has to be up a little bit. And then a minimum at x equals 6, so I'm going to put a point a little bit lower at x equals 6. Then from our second derivative number line, we came up with some inflection points. We weren't asked that, but we can tell looking at it, whenever the second derivative changes from negative to positive or positive to negative, which would be at all 3 of these points, we're going to end up with an inflection point. So at -1, we have an inflection point. It has to fall between this max and this min. So it doesn't matter where in between, but it has to fall in between there somewhere. Then we have an inflection point at 1. Again, it has to fall in between the max and the min. And an inflection point at x equals 4. So that one has to be between this max and min. Then to sketch our graph, we have to use the concavity. Our graph is going to be concave down from -3 until we get to -1. So from here to here, concave down. Then from -1 to 1, it's concave up. From 1 to 4, concave down. Oops. And then from 4 to 7, it's going to be concave up. So this is a possible graph of our function f of x.